Semiconductor Devices and Statistical Physics. University of Gujarat, Pakistan. Department of Physics. Presented to Dr. Abdul Majid Sandhu, Associate Professor. Presented by Habiba Kiran and Maria Nazir. We are enriched by technology in so many ways. It brings us closer together. Such innovations are made in educational, medical, and entertainment. These innovations are made possible by integrated circuits. Let's have a closer look to the integrated circuits. Many objects are embedded on IC, that are transistors. What are the transistors? First, I will give you the simple answer. It's just like a light switch. It turns on and off, but has no mechanical moving parts. It switches up to 100 billion times. It is on. It is 1 when it is on in binary codes and 0 when it is off. Billions and billions of 0 and 1 together make a program and a function. To compute this complex text, a group of transistors work on an integrated circuit that is known as computer chip. Microprocessors are among the most advanced integrated circuits. They control everything in computer, cell phones, and microwave ovens. Transistors can move electricity, but how they do it? Transistors are made up of silicon, a chemical element found all over the world. Silicon is a semiconductor, conduct electricity better than an insulator like plastic, not like a metal conductor. Conducted by using a process that called doping. Here is silicon atom all over the earth. Silicon has 4 electrons in its outermost shell which bounded its atoms to the neighbor. When you inject other atoms to the lattice, the silicon start behaving differently. If we dope silicon with chemical element phosphorus, the silicon has some extra electrons, so electrons flow out of it more easily. In this way, we call this n-type. If we dope silicon with another atom, with another element like boron, the lattice will have holes. So electrons flow into the lattice. It is called a p-type. By doping silicon with other atoms, we get two materials which make up a transistor. Field effect transistors or FET are electrical switches that are controlled by an applied electric field. These kinds of transistors have three major parts: the source, the gate, and a drain. The current flow from the source to the drain and gate decide whether a current flow or not. There is an oxide layer inside it. In common field effect transistor have ends of n-type material and there is a channel made up of p-type material that separate the n-type. N-type and p-type silicons are put next to each other. The free electrons from n-type move toward the p-type material to fill the holes. This creates a barrier called a depletion region. In this state, the transistor off when a positive voltage applies to the gate. It overcomes the depletion zone. Electrons are then flow from source to drain. In this state, transistor is on. This design is remarkable. We can switch on and off at ridiculously fast with no moving mechanical co-parts. Field effect transistor. There are some made up of p-type transistor. There are some common semiconductor which operate on two terminal are diode, gun diode, and IMPET diode, laser diode, LED, light emitting diode, photocell, phototransistors, Schottky diode, pin diode, solar cell, transistors, transient voltage suppression diode, tunnel diode, V cell diode, Zener diode. Now three terminals are bipolar junction transistor, Darlington transistor, field effect transistor, insulated gate bipolar transistor, silicon control rectifier, thyristor, triac, unijunction transistor. Four terminal devices are Hall effect sensor, photocoupler. Now just have a look to statistical physics of semiconductor. Statistical mechanics or statistical thermodynamics is a branch of physics that deals with the probability theory, which contain mathematical tools for dealing with a large population to study the thermodynamic behavior of the system composed of large number of particles conducted at equilibrium. N of E is the population of multiplied by probability of finding electron in conduction band, whereas P of E is the population of holes, which is equal to the density of states of holes multiplied by probability of finding holes in valence band. This graph shows the population of electron and holes at equilibrium, where Fermi level is in the middle of the valence band and the conduction band. The thermal equilibrium concentration of electrons in conduction band N naught is equal to the integral of population density of electrons in conduction band, where we use Fermi-Dirac distribution as we know that electrons are the fermions. So we use f of E is equal to 1 over 1 plus exponential E minus E of f over kT. For electrons in conduction band, E is greater than EC, which implies to E minus EF, which is greater than KT. Distribution function becomes exponential of minus EF over KT. And putting the values in N naught, we define the effective density of states in conduction band, which is equal to Nc is equal to 2 to bracket 2 by m steric and kt over h square 3 by 2, where m steric of n is the effective mass density of electrons. The thermal equilibrium electron concentration in conduction band is equal to N naught is equal to Nc exponential minus Ec minus Ef over kt. The thermal equilibrium concentration of holes in valence band P naught is equal to integral of Ec to top P of E dE, which is equal to Ec integral of Ec top GVE 1 minus f of E dE, where 1 minus f of E is the probability density for holes in valence band and is given as 1 over 1 plus exponential EF minus E over KT. For holes in valence band, E less than energy in valence band, which implies KT is less than EF minus E. By applying Boltzmann approximation, probability density becomes exponential minus EF minus E at P naught. So by putting the values in P naught equation, we get is equal to 2 into 2 pi m steric p kt over a square 3 by 2 exponential E minus EF minus EV over kt, where m steric p is the effective mass of holes. We define effective density of states in conduction band. N of V is equal to 2 into 2 pi m steric p kt over a square 3 by 2. The thermal equilibrium electron concentration in conduction band becomes P naught is equal to NV exponential minus CF minus EV over KT. Determined by parameters of effective masses and temperature. Assuming M steric N is equal to M naught, then the value of the density of effective mass of state at 300 Kelvin is Nc is equal to 0.5 into 10 to the power 9. Concentration of electrons in conduction band is equal to the concentration of electrons in valence. and P naught is equals to Pi. For intrinsic semiconductors, Ni is equals to Pi. By solving this equation, we can calculate Ni square is equals to Nc Np exponential of minus Ec minus Ev exponential of minus Eg over Kt. The intrinsic carrier concentration is nearly increasing exponentially with temperature. The intrinsic Fermi level position is in the middle of energy of valence band or energy of conduction band. Ef is equals to 1 by 2 EEC plus EV plus 1 by 2 KT natural log by 2. Electrons and holes in extrinsic semiconductors. The graph shows that the valence band has large electrons for n-type semiconductors and valence band has large holes for p-type semiconductors. And P naught are given by as n naught is equals to ni exponential of ef minus e f I over kt. P naught is equals to ni f exponential minus e f I minus e f I over kt. Naught or P naught is always a constant for a given semiconductor material at a given temperature. Matter does not hold the thermal equilibrium carrier concentration is expressed as Fermi Dirac distribution function, which is given by this equation. From where we conclude that naught t f of 1 by 2 eta t, where is P naught is equals to 2 over under root pi and V f of 1 by 2 eta f. Conductor's graph shows that the filled states of electrons and empty states of holes in the valence band and conduction band. The n-type semiconductor shows that n naught is equals to nd minus na over 2 plus under root nd minus na by 2 whole square plus ni square, where p naught is equals to ni square over n naught. Whereas p-type semiconductor shows that p naught is equals to na minus nd by 2 plus under root na minus nd by 2 whole square plus ni square, where n naught is equals to ni square over p naught. The graph shows that the acceptors from the valence band goes towards Fermi levels and the donors goes towards conduction band. While the position of Fermi energy level moves through the band gap energy depending on the electron and hole concentration and temperature. The graph shows that the energy is above Fermi energy level when electrons are added, and when energy and holes are added, the energy is low Fermi energy level. Doping concentration at 300 Kelvin, where N naught and P naught are given by these equations. The graph shows that the rate of energy of density is increasing, is linearly increasing in N-type and linearly decreasing in P-type semiconductors. Relevance of the Fermi energy. If the two materials are brought into intimate contact with what would happen to the carrier and Fermi level in these materials, the electrons will tend to seek the lowest possible energy. In this example, the electrons in materials of will state of material B thermal equilibrium occurs when the